The 1934 Chrysler Trifon was one of the most advanced and deliberately concealed experimental vehicles of the Depression era. This wasn't just a prototype. It was a rolling laboratory disguised as automotive research, testing theories decades before their time. And it challenged every assumption about what Detroit was willing to attempt in 1934. In 1934, America was still suffering through the Great Depression. Unemployment remained staggeringly high, and consumer spending had plummeted. For automakers, this wasn't just a downturn, it was an existential crisis. Many once prominent manufacturers had already vanished, with more teetering on the brink of collapse. The survivors adopted conservative strategies. Hudson, Studebaker, and even industry giant General Motors played it safe with incremental improvements to familiar designs. Innovation was seen as a luxury few could afford when merely staying afloat consumed every resource. Streamlining had begun appearing in automotive styling, but primarily as fashion rather than function. Ornamental speed lines and teardrop headlamps gave cars the appearance of aerodynamic efficiency without delivering the benefits. Most executives viewed genuine aerodynamic research as impractical academic pursuit with little commercial application. Amid this environment of restraint, Chrysler Corporation charted a different course. Under Walter P. Chrysler's leadership, the company had built its reputation on engineering excellence. Even as financial pressures mounted, Chrysler maintained what few other manufacturers could: a fully staffed advanced engineering division operating with unusual autonomy and secrecy. This division worked beyond the constraints of immediate market demands. Engineers were encouraged to explore concepts that might not reach production for decades, and in 1934, they embarked on their most ambitious project yet, one that would remain hidden from public view for generations. The Chrysler Trifon's most revolutionary aspect was its aerodynamic profile. While contemporary production vehicles typically had drag coefficients of 0.7 to 0.9, the Trifon achieved approximately 0.28, a figure that wouldn't become industry standard until the fuel-conscious 1970s. To put this in perspective, the celebrated 1934 Chrysler Airflow, itself considered radical, had a drag coefficient nearly twice as high. The Trifon abandoned traditional automotive proportions entirely. Where other cars maintained high, upright passenger compartments, the Trifon's cabin merged seamlessly into an elongated teardrop shape. Its roofline began its descent almost immediately behind the driver, continuing in one unbroken curve to its tapered rear extremity. Wind tunnel testing at Chrysler's clandestine aerodynamic facility revealed the Trifon's ability to maintain stability at speeds most contemporary vehicles couldn't safely attain. The airflow patterns photographed during these tests bear striking resemblance to computer simulations of vehicles designed 50 years later. The body featured details decades ahead of industry practice. Glass was mounted flush with surrounding bodywork rather than inset within frames. Wheel wells were fully enclosed, eliminating a major source of turbulence. Even the underside was smooth and contoured, managing airflow beneath the vehicle, a consideration completely ignored by production cars of the era. The Trifon's construction methods were equally revolutionary. Rather than the separate body-on-frame design universal in American cars, Chrysler engineers developed an aluminum-steel hybrid monocoque structure. This integrated body and chassis into a single stress-bearing unit, similar to aircraft construction of the period. This approach required entirely new tooling and assembly techniques. Documents suggest specialized equipment was created specifically for the Trifon project, then reportedly destroyed when the program concluded, one of many steps taken to maintain the project's extreme secrecy. The weight distribution was optimized for high-speed stability rather than manufacturing convenience. Unlike the front-heavy bias of most contemporary vehicles, the Trifon distributed mass more evenly between axles, resulting in handling characteristics that test drivers described as aircraft-like in their precision and stability. Powering this aerodynamic shell was a heavily modified version of Chrysler's straight-eight engine. Engineers extracted approximately 130 horsepower, a significant increase over production versions, through higher compression ratios, modified camshaft profiles, and experimental intake designs. The engine's position and orientation were altered to accommodate the radical body shape, requiring custom mounting points and a re-engineered lubrication system. The transmission, driveshaft, and differential were similarly modified, creating an integrated powertrain that complemented the vehicle's aerodynamic profile. Perhaps most challenging was the cooling system redesign. The Trifon's enclosed front end eliminated the conventional radiator placement. Engineers developed an early version of what we'd now recognize as ducted cooling, with carefully calculated air inlets that maintained sufficient airflow without compromising aerodynamics, a delicate balance rarely attempted before the 1950s. The suspension represented another leap beyond contemporary practice. The front utilized independent geometry at a time when rigid axles remained standard for American manufacturers. Documents suggest the design was loosely derived from European racing technology but heavily modified for the Trifon's unique requirements. The rear suspension implemented a trailing arm design that wouldn't become common in production vehicles until decades later. This approach allowed engineers to control wheel movement more precisely during acceleration and cornering, maintaining the optimized aerodynamic profile even under stress. The steering system required complete recalculation due to the altered weight distribution and suspension geometry. Test driver notes indicate the Trifon delivered exceptional directional stability at high speeds, while requiring significantly less correction in crosswinds than conventional vehicles, a direct benefit of its aerodynamic profile. The braking system incorporated early experiments with hydraulic assistance. While hydraulic brakes themselves were relatively new to production cars, the Trifon system went further, using pressure-multiplying servos to reduce pedal effort while improving modulation. This technology wouldn't appear in mainstream production until the post-war era. Documentation suggests only one complete Trifon was ever constructed, though several quarter and half-scale models were created for wind tunnel testing. The full-size prototype was assembled in a cordoned section of Chrysler's engineering facility, with access restricted to a small team operating under unusual security protocols. Testing occurred primarily at Chrysler's proving grounds, often during night hours to avoid observation. Test drivers were reportedly required to sign extraordinary confidentiality agreements with penalties far exceeding normal corporate secrecy provisions. During these closed sessions, the Trifon achieved sustained speeds exceeding 100 miles per hour, remarkable for any vehicle of its era. More impressive than raw speed was the stability reported at these velocities. Where contemporary cars became increasingly unstable as speeds climbed, the Trifon was described as settling into a balanced, controlled state at higher velocities. Fuel consumption figures from surviving test records indicate efficiency approximately 40% better than comparable powered production vehicles, a direct result of reduced aerodynamic drag. This efficiency advantage would have been revolutionary had it reached production, but it remained locked in classified company archives. Project documentation was tightly controlled, with much of it reportedly destroyed when the program ended in 1936. The prototype itself was dismantled, with components either repurposed for other experimental projects or deliberately destroyed to prevent reverse engineering. Several key engineers who worked on the Trifon were transferred to other divisions within Chrysler, effectively dispersing the knowledge gained from the project while keeping it within the company. This pattern of deliberate knowledge fragmentation appears repeatedly in documents surrounding the Trifon program. While the Trifon never directly reached production, its influence manifested in diluted form through Chrysler's Airflow cars. These production vehicles incorporated some aerodynamic principles tested in the Trifon, though in significantly compromised form to accommodate manufacturing realities and conservative consumer tastes. The Airflow's commercial failure likely reinforced the decision to keep the Trifon's more radical advances concealed. Chrysler executives concluded that the market wasn't ready for truly advanced aerodynamic design, a sentiment that would persist in Detroit for decades. Many innovations tested in the Trifon wouldn't reappear in production automobiles until the 1960s and 1970s. The oil crisis of 1973 finally created market conditions that made aerodynamic efficiency an essential selling point rather than an engineering curiosity. Modern computer analysis of surviving photographs suggests the Trifon's aerodynamic efficiency rivaled vehicles built half a century later. When automotive historians digitally reconstructed the Trifon's profile for computational fluid dynamics testing, the results indicated performance comparable to purpose-built efficiency vehicles of the early 1980s. The deliberate concealment of the project reflects a fascinating contradiction in American industrial culture: the simultaneous capacity for remarkable technical innovation and institutional reluctance to pursue it commercially. Chrysler possessed the engineering talent to create vehicles decades ahead of their time, yet lacked the corporate will to bring them to market. This pattern wasn't unique to Chrysler. Throughout the American automotive industry, advanced prototypes were developed and then shelved, creating an invisible history of innovation that ran parallel to the more conservative vehicles actually produced. The 1934 Chrysler Trifon proved that the future of automotive design was already understood in the depths of the Depression, waiting for a world ready to accept it. This single vehicle demonstrated that the gap between what engineers could achieve and what manufacturers were willing to produce was measured not in capability, but in courage. It stands as a reminder that innovation often exists in shadows long before it steps into light. The Trifon represents a moment when American automotive engineering briefly glimpsed its own future, then deliberately turned away. Not because the vision was flawed, but because it was too accurate, too soon. Decades of wasted fuel, compromised safety, and environmental impact might have been mitigated had the Trifon's lessons been embraced rather than buried. In this sense, the story of the Chrysler Trifon is more than automotive history. It's a parable about our relationship with technological progress itself and the complex forces that determine which innovations we embrace and which we defer. If you enjoy discovering the hidden experiments that shaped automotive history, make sure to subscribe to the channel so you don't miss our next exploration into the secret projects that Detroit tried to forget.